Hello again. Let's go to section 4, linear equations with constant coefficients. Again, basically we are looking for the solutions of this kind of equation, homogeneous case, and that kind of equation, non-homogeneous case. Wait a minute, haven't we done this before? Yes, we have, many times since chapter 2. Things like this. How did he do it then? Take Laplace transform. For each derivatives, we have all these formulas, and then solve it with respect to capital Y. The denominator turns out to be a characteristic polynomial, and then we could decompose it with respect to partial fractions. And if we take Laplace inversion to each partial fractions and add them all up, that's it. That is the solution, and that's how we used to get this problem done. This time, however, we're going to do the same equation using a different perspectives that we went through in the previous section. Basically, this is what we are going to do. We're going to find out n linearly independent solutions and take the linear combination of those. So how do we find out n linearly independent solutions? Let's begin with homogeneous case, and we begin with some educated guess. It may even look like a wild guess. Plug in y equals e to the lambda t, and then take all those derivatives using repeated chain rule. Y prime, y double prime, the third derivative, fourth derivative, all the way up to nth derivative. Because of the chain rule, nth derivative have n power, and then n minus first derivative is n minus first power, and so on. So this one will generate lambda to the nth power. That one will generate lambda to the n minus first power, and so on and so forth. So what do we get? We get this expression. This ODE becomes that if you plug in y equals exponential of lambda t. Now from here, exponential is common, so take this exponential out, and what's left is exponential times this polynomial is equal to 0. Do you remember what this polynomial used to be called? A characteristic polynomial. So setting this characteristic polynomial equal to 0, we get this equation which we call a characteristic equation. The solutions of this characteristic equation is called characteristic value or eigenvalues, and the solution will be e to the that eigenvalue t. In general, we're going to get something like this. If we have all those distinct eigenvalues, then you're going to get all these distinct solutions which happen to be linearly independent. Yes, we can prove those rigorously using Wronskian. And then add them together, take linear combination, and that is the general solution. What if we have some multiple roots? For example, if we have lambda minus alpha to the third power, kind of like that, in that case, you're going to get some exponential, t times exponential, t squared times exponential, and so on. It'll run all the way up to t to the n minus first power, k minus first power, excuse me, if the multiplicity is k. And then we have kind of this part in the general solution with appropriate coefficients. And this thing corresponds precisely to the same idea in partial fraction theory. You have multiplicity 3 down here, then we have these 3, and take the Laplace inversion, we used to have these 3, and exactly the same thing took place. What about complex roots? In that case, we have to have a pair of complex conjugate roots. The reason it has something to do with fundamental theorem of algebra, where everything can be factorized all the way up to first degree in complex numbers. But then again, everything here is real, so if you take conjugate, everything stays the same, and that's why we have this plus and minus complex conjugate. For the detail, you can take some algebra course, or you can ask your absolute algebra teacher. Anyway, this is a conclusion, and therefore we're going to have a pair of complex exponential, and if you have multiplicity, t times that, t squared times that, and so on and so forth. Now, there is a little bit more pleasing way in terms of real function to express those complex exponentials using sinusoid. Instead of e to the alpha plus beta it, e to the alpha minus beta it, we can express those as exponential cosine plus exponential sine, kind of like that. And then t times those, t squared times those, will take care of those multiplicities as well. Let's go through an example. Let's solve this homogeneous equation. Holy cow, how do we handle that? Well, don't panic, I'm going to use technology. So the characteristic polynomial is just 9th power, 8th power, 7th power, and so on. So here's a characteristic polynomial. And if I factor it, I'm going to get this kind of beautiful factorization. Let me expand the font. So s minus 2, and then s plus 1, and s squared plus 4s plus 5. Multiplicity 2, multiplicity 3, and then multiplicity 2. And by the way, if you set them equal to 0 and get eigenvalues, here they are. So the conclusion is, we have lambda equals to 2, double root, and lambda equals to -1, triple root. And then, oh, as a matter of fact, I forgot plus or minus here. Okay, minus 2 plus or minus I, we're going to get double roots here. And double root because this second power, triple root because this third power, and double root because this second power. Okay, all right. And thus, we'll have this kind of expression. Double root, so we have exponential and t times exponential. Triple root, so exponential, t times exponential, t squared times exponential. And then complex, so we have exponential cosine times exponential sine. And then double roots, so we have t times those as well. By the way, I just recycled exactly the same problem that I did already in section 0 over here, down here, this one here. It's the same type of problem except that this was homogeneous, so I don't have this non-homogeneous particular solution part. The blue, green, and purple correspond precisely to the same colors in this problem down here. Of course, in reality, you're going to be dealing with a much simpler problem when you're doing this in paper and pencil method. But I wanted to show you the general case with some distinct eigenvalues and how to deal with multiplicities, how to deal with complex, and so on and so forth. Okay, how about some non-homogeneous case? In that case, we just look for some particular solution and we use some educated guess, and a lot of people, a lot of smart people over the centuries, as a matter of fact, tried various, and they already found out what are the best educated guesses. And you can use this kind of term. By the way, this table came from some other textbook, but I think we can use it. Okay, let's see. Here's an example problem. Okay, the same homogeneous part, which gave us, let's see, these eigenvalues, lambda equals to 2, -1, and -2 plus or minus I. Okay, all right. And here, we don't have any overlap here, and then we have eigenvalue 5 from this particular solution. So, okay, we're going to take 8 times e to the 5t power, and then we're going to plug it in here. So take the derivative 9 times 8 times 7 times and so on, using the chain rule multiple times. You're going to get this. Take the chain rule 9 times, so we're going to get 5 to the 9th power. And then coefficient a was there before, coefficient 4 was there before. Similarly, we get 5 to the 8th power here, because we used the chain rule 8 times this time. And so on and so forth. Oops, I forgot the term 75 here. Okay, alright. Now it's good. This one corresponds to that. And from this equation, solve for a, exponentials are all common. We can cancel out. And what do you get? We get this equation to solve. Difficult to solve, but for the computer, it's an easy job, just computation. So 1 over 259 something, and that's your a, this value here. That means this is the particular solution. If you put it like this, then this solution satisfies this original non-homogeneous equation. So this is yp part. And then the general solution looks like yp plus general solution for homogeneous case. So we can recycle what we did earlier. So this is what we just did. And then all the others were just taken from homogeneous. Let's check. I rewrote all those to this Mathematica program, and then I'm asking Mathematica to calculate the left-hand side of that differential equation. All these. Please note that in this Mathematica command we have 9th derivative, 8th derivative, and so on. Pretty complicated, but the computer can handle it in no time. 75 e to the 5t power, which is precisely what we wanted to begin with. So everything fits. All is well. And in conclusion, or in summary rather, we can say that the educated guess to find a particular solution is some coefficient times whatever the exponential. We have, of course, other kind of examples too, as we have in this table. Instead of just exponential, yeah, we use that one. If we have some more complicated, some polynomial type exponential or something, you may have to do things like this. And of course, you have more coefficients to find, which means bigger system of linear equations later on. Sine and cosine go kind of like this, and so on and so forth. Okay, let's go to the next example. This time, same equation, equals to 27 e to the 2t power. How about that? There's a bit of a problem. We cannot select yp as 8 times e to the 2t power. We can't do that because e to the 2t power, e to the t times e to the 2t power, they were already taken. Let's see, where is the homogeneous equation? Yes, they are already taken. So in order to avoid this overlap, we go one higher power, so t squared e to the 2t power. Do you see? E to the 2t power, t times e to the 2t power, they're already taken. So we can't use those. So we go with t squared times e to the 2t power. And then plug those in and calculate all those derivatives using product rule and chain rule all the way up to 9th derivative. Good luck trying to do any of those. I don't think anybody is stupid enough to try that. Instead, let's do this using computer algebra system. It works out. Let's see, what did I do? This is equation, differential equation. Yeah, we have 9th derivative, 8th derivative, and so on. And then is equal to 27 e to the 2t power. And then coefficient a is what we are looking for. So comma a, and what did you find out? 1 over 2312. Okay, all right. And that is the coefficient that I have found out. So what's the deal? This is a particular solution, and we can check that with mathematical program, but that can wait. Let's get the general solution first. This is particular solution, and the homogeneous equation has this as a general solution. We saw that already. So that's a particular solution. The rest is the general solution for homogeneous equation. Put them together, we get the general solution of this non-homogeneous equation. We can check with this mathematical program. We have first clear the variables, and then define your function, and then here's the left-hand side of that differential equation. 9th derivative, 8th derivative, 7th derivative, and so on. Everything is here. And run it. What do I get? Do I get the right-hand side? 27 e to the 2t power? Yes, we did, which means we did it right.